So in these lectures, I will present a course in probability theory. So in this first lecture, I will just introduce some notation and present the first basic results. So I will assume throughout these lectures that you know measure theory. And the setup will be the following. We will have a triple where omega will be an abstract space, F a sigma algebra of subsets of omega, and P a probability measure defined on the sigma algebra F. This means that P it's a measure, so it means that it's a function from the sigma algebra to the non-negative real numbers, and which may assume the value plus infinity. So what does it mean that P it's a measure? Remember, well, this function has two properties. The first one is that P of the empty space, empty set, it's equal to 0. And the second property is that this function is sigma additive in the following sense. If you take a family Aj of elements of F, which are disjoint 2 by 2, so if you take J different from K, the intersection of Aj with Ak, it's equal to the empty set, then the probability or the measure of the union of the sets Aj, it's equal to the sum of the measures. So these two properties define a measure. And now we will introduce a further property of these measures, that it is a probability measure, and that means that the measure of the full set omega it's equal to 1. So that will be the setup. We will always have this triple, which I will call a measure space or probability measure space, and we will be working on this context. So now on this space we will define what's called a random variable. So a random variable will be a function x from omega to r, and the space R we will endow it with the Borel sigma algebra. So B will represent this sigma algebra, which is the smallest sigma algebra which contains the open sets of R. And a random variable in this course will mean simply a measurable function. So a function x from omega to R, which has the following property, that if you take the inverse image of any element of B, it belongs to the sigma algebra F. So this means that for all Borel set A, the inverse image of A by X, it's an element of the sigma algebra F. Remember that this set represents the sets of all omegas in omega, such that X of omega belongs to A. So in the context of probability theory, measurable functions are called random variables. So now let me introduce the probability distribution measures. We have a random variable x defined on a triple omega fp, and I will present by mu x the probability distribution measure associated to the random variable x. So this is a probability measure defined on the Borel sets of R. And how is it defined? Fix a Borel set A, mu x of A, it's the probability of the inverse image by x of A. So x, it's a random variable, so it's measurable from F to B, which means that the inverse image of a Borel set by x belongs to F. So this probability is well defined because this is an element of the sigma algebra A, F. And how, what this set means, let me recall you, it's just the set of omegas for which x of omega belongs to A. So instead of writing this long expression, I will just denote it simply by probability that x belongs to A. So this means that when I write this formula, I'm meaning that I'm computing the probability of the sets of omegas such that x of omega belongs to A. And as I said, this is well defined because x is a random variable. Now I ask you to show that indeed, as an exercise, mu x is a probability measure defined on the Borel sets of R. And this is what's called the probability distribution measure associated to the random variable x. Now I will define the distribution functions. So fix again a random variable x defined on a measure space. And I will define the distribution function associated to x, and I will represent that by f of x. So this is a function from R to 0, 1, the interval 0, 1, and which is defined as follows. So fx of x is the probability that x is less or equal than x. So this is the inverse image of minus infinity x, the interval minus infinity x closed at x. So this is a Borel set. So this expression is well defined. And mind here that I'm taking less or equal to. So certain authors will define the distribution functions in the following way, taking x strictly less than x. Here we will adopt this convention. And what I want to stress now is that this distribution function has some properties, and I leave it to you to check them. First is that the distribution function, it's monotone. So in the sense that if x is less or equal than y, then fx of x is less or equal than fx of y. Then the second property is that fx it's right continuous. And it's right continuous because I adopted this convention. So fx is right continuous. And of course, since it is monotone, it has left limits. So I'll just say that the function has left limits, but it's right continuous. And finally, since x is a random variable, we have that the limit as x tends to plus infinity of fx of x, that this is equal to 1, and the limit as x tends to minus infinity of x, that this is equal to 0. So I ask you to check these three properties, and if a function f has these three properties, we'll call it a distribution function. And so this is the distribution function associated to the random variable x. There is a one-to-one correspondence between probability measures mu defined on the pair RB and distribution functions. So probability measures and F distribution functions. So what I'm claiming is that there is a one-to-one relation between these two. So assume that you have a probability measure mu defined on RB. You can define now the distribution function fx by taking the measure of the set minus infinity x. So here I should write that I'm taking the measure of this interval, but that will be too cumbersome, so I'll just denote the measure of this set by this symbol. So if I define fx by this formula, I claim that the function f, so defined, is a distribution function. And I leave it to you to check that indeed this function has the three properties I just erased. Now assume that you have a distribution function f, and you want to construct a measure on the Borel sigma sets, the Borel sets of R. Well, I will define mu of the interval AB, and here A and B are such that minus infinity might be equal to a, which is less than b, which is less or equal than plus infinity. So if you take a and b with satisfying these conditions, I will define mu of ab as fb minus fa. Now, the family of such sets, so if I call S the family of all intervals a, b, where a and b satisfy this condition, which means that minus infinity is less or equal than a, which is less than b, and b is less or equal than plus infinity, that this forms a semi-algebra. Again, I assume that you know what a semi-algebra means, and I leave it to you to show that mu is sigma additive on this semi-algebra. So, as an exercise, prove that mu is indeed sigma additive on S. And once you prove that, you can use Kara-Theodori theorem So you can use Kara-Theodori extension theorem to extend the definition of mu to the sigma algebra generated by such sets, but the sigma algebra generated by this set, it's exactly the Borel sigma algebra. So you can use Kara-Theodori to extend mu to b. And therefore, in this way, you will construct a unique, because this extension is unique, measure mu on that set, and it's clear that the measure of r is equal to 1, because if you take here a equal to minus infinity and b equal to plus infinity, you get from this equation that mu of r is indeed equal to 1. So you see that there is a one-to-one correspondence between probability measures defined on the Borel sets of R and distribution functions, and that this one-to-one correspondence is given by this equation or that equation. So up to this point, we introduced random variables, probability distribution measures, and distribution functions, and we have seen that there is a one-to-one correspondence between distribution measures and distribution functions. Now I want to present several types of distinct distribution functions, and for that I will define what are discrete random variables. So I'll say that x it's a discrete random variable if and only if there exists a countable set B, so B subset of R which is countable, such that the probability that x belongs to B it's equal to 1. So if there is a countable set B such that the probability that x belongs to B is 1, we call x a discrete random variable. And we can extend this definition to distribution functions. So I'll say that a distribution function f is discrete if and only if a similar property holds, so that there exists a countable set B. So let me write B as a set of xj, j larger or equal than 1. And there exist also weights pj, again j larger or equal to 1. So these weights should be non-negative, and the sum, they should sum to 1, such that the value of f at x, it's given by summing these weights for all j such that xj it's less or equal than x. So I'm summing over all j such that xj it's less or equal than x pj. So first I ask you to show that fx defined in this way, it's indeed a distribution function, so it satisfies these three properties. And next, that if x is a discrete random variable, then its distribution function is discrete. So this is left as an exercise. Now we introduce discrete distribution function. Let me define two more types of distribution function. First, I'll say that a distribution function f is absolutely continuous if there exists a measurable function f from R to R plus. So note it's non-negative such that fb minus fa it's equal to the integral from a to b of ft dt. So if there exists a measurable function, a non-negative measurable function f for which fb minus fa is equal to this integral for all a less than b in R, then we will say that the distribution function is absolutely continuous. Observe that, and again, this is known from measure theory, but I ask you to check it again, that if f is absolutely continuous and satisfies this equation, then f is differentiable almost everywhere, at almost every point with respect to the Lebesgue measure, and its derivative f prime it's equal to f. So this is again an exercise in measure theory, which I ask you to try. So this is a definition, and then let me give you a second definition. A distribution function f is said to be singular so here I'm defining singular, here I defined absolutely continuous, if and only if, well, f it's continuous, f it's monotone, so you know that a monotone function is differentiable at almost every point, and I will require here that the derivative of f, that this derivative is equal to 0 almost everywhere. So at first sight it might be difficult to conceive a function which is continuous, whose derivative is equal to 0 almost everywhere, and which increase from 0 to 1, let's say in an interval. So I'll give you in the notes reference in which you can find the construction of a singular distribution function. I can just give you a hint. If you take the interval 0, 1, you want the function to be 1 at 1 and 0 at 0. So what you do is to define the Cantor distribution function is that you divide this interval in 3 intervals of the same length, and you define now the distribution function in the middle interval, saying that taking the average of these two values. So let's say that you will define the distribution function in the interval 1/3, 2/3 as the average of these two values, which is 1/2. And now you continue the procedure. Now you have 2 intervals left. You divide each one of these 2 intervals in equal length intervals, which now have size 1/9. And in this middle interval, you define the function as the average of the values in which the function has already been defined. So in this middle interval, you define it as 3/4, and you do the same thing here as defining it as 1/4. And you proceed in this way, and at the end, you show that indeed this function is continuous, and its derivative is equal to 0 at almost every point. So this is the Cantor distribution function, and I will give you reference in the notes in which you can see a full proof of this construction. And also, if you go to the lectures, the video lectures on measure theory, I constructed this distribution in one of these lectures. So I defined three types of distribution functions: discrete ones, absolutely continuous, and singular ones. And there is a very nice theorem which tells you that essentially all distribution functions are combinations of those three. So if you take, the theorem reads as follows: take f a distribution function, then f can be written as a convex combination of those three types of distribution function. So this means that f can be written as alpha fd plus beta fac plus 1 minus alpha minus beta fs. So this theorem is telling you that there exists alpha, which is non-negative, beta non-negative, and such that alpha plus beta it's less or equal than 1, in such a way that alpha, beta, and 1 minus alpha minus beta represent a convex combination of these three. So there exists alpha, beta satisfying these equations, and there exists a discrete distribution function, an absolutely continuous distribution function fac, and a singular distribution function fs, such that f can be written as a convex combination of these three distribution functions. Again, I will not prove this theorem here, but you will find in the notes reference to this result. I will now define expectation of a random variable. So we are working on a measure space, omega fp, and we have a random variable x. So x, it's a function from omega to r, which is measurable. I will assume that x is integrable with respect to p, so that the integral of the absolute value of x is finite. In this case, I will define the expectation of x as the integral of x dp. So expectation of x, it's just the integral of x with respect to the measure mu, and this is well defined if x is integrable. It's also well defined if x it's a non-negative random variable. If x is non-negative, I can also define the expectation through this formula because, well, this is always defined. Of course, it can take the value plus infinity, but it's certainly well defined. And now I ask you as an exercise to prove the following identity. I ask you to show that the expectation of x it's also equal to the integral in R now of x mu x dx. So remember, mu x represents the probability distribution of the random variable x, and you have to show that under the assumption that x is non-negative or that x is integrable, that these two quantities are equal. In the first case, they are finite, so both are equal to a real number, and this real number is the same. In this case, if one of them is equal to plus infinity, then the other is equal to plus infinity, and otherwise, if one of them is finite, the other is finite, and you have, and the identity holds. So I ask you, again, as an exercise to prove this identity. So up to now, this lecture was a review of measure theory, and now we have the first result, which goes beyond measure theory and use the fact that P is a probability measure. So I have x, a random variable. I'm assuming that it's positive, so it's non-negative, and I want to claim that the expectation of x it's finite if and only if a sum is finite. So what I claim is that this expectation is larger or equal than the sum for n larger than 1 of the probability that x is larger or equal than n, and that this is it's bounded by 1 plus this sum. So these bounds can be useful if you want to prove that a non-negative random variable has finite expectation, has finite interval. You just need to prove that this sum is finite, and this is a necessary and sufficient condition due to these inequalities. So this is the result which I want to prove. So let me first prove this inequality, and to prove that inequality, let me start by considering this sum. So I have here a sum of probability x larger or equal than n. Well, if x is larger or equal than n, I want to write this as a sum for j larger than n of the probability that x belongs to the interval j plus 1. Right, because the union of these intervals for j larger or equal to 1 is the interval n infinity, these two expressions are equal, and now since this probability is non-negative, I can exchange the order of summation, and here I get that a sum for j larger than 1. This does not depend on n, so it's the probability that x belongs to j plus 1. And here I have a sum from n from 1 up to j, so that gives me j. So this is an identity. We didn't do much up to now. Now let us rewrite this probability as an integral. So I have a sum for j larger than 1, and here, instead of writing this probability, I will write it as in the following way. This is the probability that x belongs to the interval dp. So what do I mean here? Chi a will represent the indicator function. So a, it's a Borel subset, and chi a of b of x will be equal to 1 if x belongs to a and 0 otherwise. So this function, it's called the indicator function of the set. It takes only two values, 1 and 0, 1 at the points at a and 0 in the complement of a. So you see that this integral, well, this function takes the value 1 if x belongs to this interval and 0 otherwise. So this integral corresponds exactly to the probability that x belongs to this interval. And now I have j, and you see that in this interval, x, it's larger than j and smaller than j plus 1. So j, it's bounded by x. So this expression becomes an inequality if I replace j by x. And once, so maybe let me do it in 2 steps. I still have here, say, j, and what I'm bounding now is that, well, j, it's less than x in this interval, if x belongs to this interval, so this is less or equal than the sum for j larger than 1 of the integral of x, chi, so the indicator function of the interval j plus 1 of x dp. And now I can sum over j, and when I sum over j, since these intervals are all disjoint, all these expressions are positive, non-negative, so I can exchange the sum with the integral, and once I place the sum inside, the sum of all this indicator function, it's equal to the sum of the interval 1 plus infinity, because the union of these intervals is given by that, and this is bounded by 1. So this is clearly less or equal than x dp, and this is exactly what we represented by expectation of x. This is the expectation of x. So we have here a proof of this first inequality. Now let's go prove the second inequality, and for the second inequality I'll just use this black bolt and we'll go in the other direction. So I'll start here with the expectation of x, which is the integral of x dp, and I'll say, well, that this is equal. I will cut the interval 0 infinity, so now I'm here interested in the interval 0 infinity as this union of intervals j plus 1, but the difference now is that I need to take the sum starting from 0, right? So I first wrote chi, x, then I introduced here the indicator of the interval 0 infinity because x, it's non-negative, so there is no difference by taking x or by taking x multiplying the indicator function of the interval 0 infinity. Once I introduced the indicator of 0 infinity inside this integral, I can rewrite this interval as the union of these intervals for j larger or equal to 0, and therefore writing this indicator as the indicator of this union, the indicator of the union is equal to the sum of the indicators, and now I can place the sum outside of the integral because everything is non-negative. So up to now we have a sequence of identities. So we arrived at this point as before, but now we have a sum for j larger or equal than 0. Now in this interval x belongs to the interval j plus 1. So this means that x, it's bounded by j plus 1. So I can get an upper bound for this interval replacing x by j plus 1. So you see that we have essentially the same expression. The difference is that now our sum starts from 0, and instead of j we have j plus 1. So since everything here it's positive, I will divide this expression in two, one which is the sum in j and one in which I keep 1. So the one in which I have the sum in j is this one. It's exactly that one, and then I have an extra which comes from the 1, and the extra tells me that I have a sum for j larger or equal to 0 of the indicator of j plus 1 of x dp. So this is now an identity. I divide this expression in two, one which takes care of j, the other which takes care of 1. The one in j is this term, and the one with 1 is this one. So let me consider first the first one. Again, I can place the sum inside because everything is non-negative, and once I have the sum inside, I can use again the fact that the union of these intervals gives me the interval 0 infinity, and therefore so I can write that this it's equal to, let me write it here as the indicator function of 0 infinity of x dp. Now the indicator function, it's always bounded by 1, so this is bounded by 1. So the extra term we proved is bounded by 1. So now we have to estimate the other term, in which the only difference with respect to our previous, the first part of the proof, is that here we are starting from 0, while before we started from 1. But since we are multiplying this expression by j, there is no difference in starting the sum from 1 and starting the sum from 0, because the zero terms give you no contribution. So I can replace this sum of j larger or equal to 0 by j larger or equal to 1, and then go back in our sequence of identities and to obtain that this expression is actually equal to that expression. So what did we prove? We proved that the integral of x dp, it's bounded by 1, which is the red term, plus this sum, which is this sum, which takes care of the white term, and that proves the second inequality. So, as I said, we have here two bounds which are very similar for non-negative random variables. In particular, if you want to prove that the expectation of a non-negative random variable is finite, you have to prove that this sum is finite, and this is a necessary and sufficient condition for this expectation to be finite. So you are not trying to prove something harder by proving that this sum is finite if you want to prove that the expectation is finite. I ask you to prove the following corollary of the previous result. Assume that x is a random variable which takes only integer values, so that the probability that x belongs to the set 0, 1, 2, and so on, that this is equal to 1. Then I claim that the expectation of x is equal to the sum for n larger or equal to 1 of the probability that x is larger than n. So in the case in which x takes only integer, non-negative integer values, the expectation is exactly given by this sum. Now let me make a comment. So assume that there is a measure space and that we have a random variable defined on this measure space, and that we have a function from R to R which is measurable. And here I will always adopt the Borel sigma algebra. So when I say that f from R to R is measurable, it means that the inverse image by f of any Borel set is a Borel set. So then I claim, I ask you to check that f of x, which is now a new function from omega to R, which is obtained as the composition. So this is the composition of x with f. So you first apply x and then you apply f. That this is a new random variable. So what I claim is that if f is measurable, f of x is again a random variable. So I ask you to check that, and once you prove that, then prove the following theorem that, well, if you have, again, under the same hypothesis that we have a measurable space, a random variable, and a measurable function, then the following holds. The integral of fx dp. So here I'm taking just f, applying x, and considering the integral of this object on omega, that this is equal to the integral on R now of fx mu x dx. So here mu x is the probability distribution of the random variable x. So this is a measure on R, and what I'm asking you to prove is that that this integral is equal to that one. Of course, here I need these integrals to make sense, so I'm assuming here that both of these quantities make sense, so either that f is non-negative or that these two objects are integrable, so either f non-negative or that the integral of the absolute value of fx dp is finite, and that the integral over R of fx mu x dx. It's finite. So what I want you to prove is the following. Assume that f is non-negative, then this identity holds. Or assume that this quantity is finite and this quantity is finite, then this identity holds. And this is a simple exercise in measure theory. So let me complete this lecture with two inequalities which are extremely useful. The first one is Jensen inequality. So Jensen assumed that phi is a convex function. So phi is defined from R to R. And I'm assuming that it's a convex function. So just to remind you, convex means that if you take any convex combination of 2 points, so let me take theta in 0, 1, and saying that phi is convex, it's to say that f of theta x plus 1 minus theta y is less or equal than theta phi of x plus 1 minus theta phi of y, and this for all theta in 0, 1, and for all x and y in R. So let's assume that we have a convex function. Let's assume that we have a random variable, and I will assume that this random variable is integrable, which means that the expectation of the absolute value of x is finite, and I will also assume that the expectation of phi of x is finite. So under these two conditions, what I claim is that if you take phi of Ex, so Ex it's a real number because we have this condition. Now I can take phi of this real number, and that this is bounded by the expectation of phi of x. So we have this inequality provided phi is a convex function. Let me provide you a proof of this inequality. And as I said, this inequality will be used several times. So let me take a point x0 in R. And what I claim is that since phi is convex, there exists a linear function, which I'm representing by Lx. So L of x, it's linear. And with two properties. First, the value at x0 of L and phi coincide. So L of x0, it's equal to phi of x0. And then phi, it's strictly, it's above L at all points. So L of x, it's less or equal than phi of x for all x in R. So this is saying that, well, if you take a convex function, if you take any point of the convex function, then you can find a linear function which coincides, whose value at that point coincides and which is below. So you see another convex function, and here you have plenty of linear functions which satisfy this property. So I'll give you a reference in the notes in which you can find a proof, or I'll give you a proof of this fact. And I will use this fact in order to prove Jensen's inequality. So since L is linear and it's a linear function defined on R, L can be written as LB plus X. But now by using the fact that L is equal to phi x0 at x0, this means that I can write L as phi of x0 plus some constant c times x minus x0. Okay, so this is the expression of all linear function which at x0 it's equal to phi of x0. And I know that this expression by the fact that phi is convex, it's bounded. So I know that there exists a C for which this inequality holds for all x in R. So now let me use this inequality in order to prove Jensen inequality. And what I will do here is that I will use x0. I'll take x0 to be the expectation of x. By taking x0 as the expectation of x, what this inequality is telling me is that phi of the expectation of x plus this constant c times x minus the expectation of x, that this is bounded by phi of x. And this holds for all x in R. Since it holds for all x in R, I can replace x by the random variable x, and I get that this inequality holds for all omega now. Well, but since it holds for all omega, I can just integrate both sides. I can integrate both sides because, well, this is a real number, so it gets out from the integral, and x, this is a constant, x, it's integrable, so this integral makes sense. And when I take this integral, what I get is the expectation of x minus the expectation of x. So this piece will cancel, and here I get the expectation of phi of x. So by taking the integral on both sides of this inequality, I get exactly this inequality because, well, the integral of a constant with respect to a probability measure p, it's equal to that constant. So I get here phi of ex. The integral of this second piece is 0 because I'll get c times the expectation of x minus the expectation of x. And on the right-hand side, I'll get the integral of phi of x, which is the expectation of phi of x. And therefore, this completes the proof of Jensen's inequality. So let me conclude this lecture with the Chebyshev inequality. So Chebyshev inequality reads as follows. You take x, a non-negative random variable, and f from R plus to R plus, a monotone non-decreasing function. So here I'm asking that if x it's less or equal than y, then fx it's less or equal than f of y. And what I claim, what we want to prove, which is Chebyshev inequality, is that the probability that x it's larger than a, it's less or equal than 1 over f of a, the expectation of f of x. Note that this is well defined because f it's non-negative, might be plus infinity, but it's always well defined, and that his inequality holds for any function f which is well, monotone, non-decreasing, and positive. So let's prove Chebyshev's inequality. That's very simple. Since x it's larger than a, and since f it's monotone, this implies that f of x it's larger than f of a. So this probability it's less or equal than this one because, well, if x, this set, it's contained in this set. Because if x it's larger than a, since f it's monotone, then fx it's larger than f of a. And I can write this probability as the expectation of the indicator function of the set that fx it's larger than fa. Remember, chi is the indicator, so this is equal to 1 on this set and 0 on the complement, so the probability coincides with the expectation of the indicator function. Now, on this set, fx it's larger than f of a, which means that 1 it's smaller or equal than fx divided by fa. Right, on that set, fx it's larger than fa, so I can divide that by f of a to get this inequality. Now, of course, if f of a is equal to 0, well, this doesn't have a meaning, so I'm assuming here that f of a it's strictly positive. And since it's strictly positive, I am allowed to divide. Now here I can think that there is a 1 multiplying this indicator function, and that this 1 is bounded by this expression. So this means that this integral here, it's bounded by fx divided by fa times the indicator of fx larger or equal than f of a dp. And since these quantities are non-negative, I can just say that this indicator function is bounded by 1, and therefore I have that this is a constant, can be moved out of the integral, and what remains is that this is fx dp, which is exactly the expectation of fx divided by fa. Mind on the way, by the way, that we proved a slightly stronger inequality, so that we can introduce here, if you wish, this indicator. So we have a slightly stronger inequality, which tells us that the probability that x is larger or equal than a, it's bounded by 1 over fa, the expectation of fx multiplying this indicator function. But I have to confess that in all my life I've never seen this indicator being used. So usually Chebyshev is used in this weaker form that I just presented. And with this, I complete this lecture.